Okay, fatigue is the next major thing to consider with your welded or with anything with design and engineering. So fatigue in welded connections, voids, additional reinforcement, all sorts of the defects are all likely to be points of stress concentration. And stress concentration is obviously where our fatigue starts or initiates in the high cycle or low cycle fatigue. Just a bit of revision, you would have come across this sort of diagram in second year. And so this is a rotating beam, and they basically get it's a very clever little design where they get a little cotton reely type thing. And I'm not going to try and draw the mirror side of that. But this is all super finished, lovely polished, and the machine actually puts a bending moment in this thing as it rotates without putting a shear load, which is pretty clever. So it's a pure bending test, and from that you get all of these points that make up the fatigue life. Okay, and if you're looking at a carbon steel, and by that I really mean any of the steels that are not stainless or that sort of thing, you will end up with a fatigue life curve that goes from 1,000 cycles to 1,000,000 cycles to 10 million cycles, etc. And there is often a knee point at about 1,000,000 cycles where all of a sudden, as long as you're below that level, you can just keep using it forever and ever. If you happen to be operating at this sort of a stress level, then you're likely to be thinking about it breaking at around about 20,000 cycles. Okay. Now this surface is super well made and polished and everything else, so it's a perfect specimen, if you like, which means of course we need to do modifications to make it useful for what are less than perfect conditions. So if you look through the textbook, you'll find that there is an endurance limit, SE, that is a function of all these different Ks, modification factors, times by what the endurance limit defined by this sort of a test gives us. Surface condition, size, load, temperature, reliability, we'll talk a little bit about them as we go through. So when we're looking at cyclic loads and things, I guess the important thing here is the mean and the amplitude of the cyclic stress. And so it doesn't need to be always one side. It doesn't always need to be all tension or all compression. It can straddle. And so you can have a case where you have a zero mean stress and it's fully fluctuating around that 0 point, okay? Through to a case where you've got a very high preload and all of your amplitude is way up there. So you've got a sigma M and then a little tiny sigma A on top. If we're trying to work out where we sit, the Gerber and Goodman and type diagrams are a big help for this sort of stuff, where we can put, this here is sigma A, this is the mean in tension and in compression. We can put the yield point, right, as one of our main boundaries. If it's a ductile material, then that yield point will be the same in both directions. Okay, if it's a brittle material, that's a different sort of analysis, and I point you back to the book. We have here a number of different number of cycles before failure, and they will influence what load we can put on things. So for an awful lot of stuff we do in engineering, you really are looking for an infinite life, 1,000,000+ cycles. But if you're designing for Formula One motorsport, for example, you might have data that shows a particular component that for its life only does 1,000 cycles. And so therefore, you're better off optimizing it to do 1,001 cycles and save a few grams. Same in aerospace. If you really understand what your product is doing, then you can much more tightly optimize it. But if we assume we're going for a 10 to the 6, then we can create, this tent. We then look at the Goodman line. Let me do it in orange. Goodman going from there to there. And so if we live or work within that area, I'll do it in attention, then we should be okay. It's not going to break. Now, of course, of course, right, if we increase our load or whatever, let's say we work in here and we predict this is the maximum load. So the ratio of 1/2 is going to be a factor of safety, basically, or the reciprocal of factor of safety. Depending on how close you want those two to line up, really changes your duty of care about how accurately you're going to do some of these things. So whilst we've got the modified Goodman line, which is this guy running down through here, there are other curves that tell you, and this is going to be hard to draw. These are elliptical curves that give you actually a little bit more headroom there for how high you can stress things. But of course, the closer you get to that, the more probability that you might run foul of the statistical variance of the experiments. So again, as I've said before, for a couple of things, this is a simplification of a complex situation. This gives you an insight into it, but if you're doing this seriously for a Formula One or an aerospace team or whatever, then you'd really want to go and look your books up again. So if we're not yielding the material, and that's certainly, you can yield the material. Ordinarily in engineering, in mechanical, we would say if you've yielded it, that's it, it's game over. It's not completely true. It's the very conservative and safe way to do things. But if you look at fluctuating axial stress, these are different mean stresses out along this direction. So if I've got, that will fail after 1 million cycles. Noting here is the yield strength out along there. So this guy on first stress is going to be okay, and he keeps just missing that yield line. So I'm not going to yield it, but I'm running it at a higher average stress level. All right. Sorry, that's sigma m there, sigma m and sigma a. But if we come over to here, I've immediately yielded, and I'm going to continue and then put that on it, and I'm still going to get my 1 million cycles worth of life out of the thing. Now I'm going to stretch or deform in that initial first loading, right? But then it should elastically relax. Now, again, you're starting to talk about design areas that you want to have a lot of experience in before you commit to having people's lives hanging off that. So, fatigue in welded connections. You've got to consider a whole heap of different things here. So, the toe of a weld, the end of a parallel fillet weld. So I mentioned earlier that if let me just draw. If I pick up my welder and I strike an arc and I start welding along this way, well, when I very first start that arc, this material here is cold. By the time I get moving a little bit, I've got heat running away in all of those areas. So I'm getting that metal ready to accept the weld. And so this first little bit of weld here is probably not going to be as good as a little bit into it. Same time, by the time I get down to this other end, I run out of metal on the parent metal to absorb the heat, so it may overheat a little bit, but it's also where I stop the arc, and so I may get a little bit of less fill in my weld. So I might have a cold start, and I might have an underfilled end. So we've got stress concentrations, basically, at the ends of the welds. So there's all sorts of things that you need to be thinking about. And in fact, the other way to deal with this guy is if you've got, say, 100 millimetres of weld, and it might be a 6 millimetre weld, then you ignore the first couple of diameters on each side. So that becomes effectively, say, like an 85 millimetre weld that you do your analysis on. So, example as always, 2 steel plates butt welded. Plate and welding materials have known strength properties. We put a fluctuating load between -20 and +60, so between compression and tension, with a factor of safety of 2.5. The assumed 95% reliability comes into it in terms of picking a factor of one of the Ks. So if the weld reinforcement is not removed, and what if we grind it off? Now, when we're talking about grinding it off, it's not just, pick up an angle grinder and go nuts. Because what you want to avoid is, if I can sort of three-dimensionalise this drawing a little bit, you don't want grinding marks running in that direction because they're just stress concentrations. All right? When we're talking about ground, what we're really talking is a nice fine grind that's in the direction where the stresses are going to work, so there are no stress concentrations to precipitate a failure. So again, carefully ground to provide a smooth, continuous surface. Okay, so if we assume the weld is not ground, weld metal has a rough surface compared to an as forged, let's say an infinite, which is 10 to the 6 cycles. We can do some estimations. So we know that the endurance limit is not going to be, we may not have endurance limit for this exact piece of material. So what we can do, and there's R.R. Moore suggests, for an ultimate strength less than 1400, which is most of what we work with, use half of its ultimate, right? 0.56 forged, 1 axial loading, and we end up with the right values. So I'll go through those. Surface factor, there's this equation where you put in parameters. There's your A and your B to give you this number of 0.56. Okay, you just work through, these are all straight out of Boundy. It's an axial load, so that tells us there's no size effect, etc. So KB equals 1. There's some charts there. Table 6.3 helps you pick those numbers. Loading factor, again, just read the tables. Temperature factor is an interesting one, just as a side note, because up to, in this case, a couple of 100 degrees, it actually gets better when it gets a little bit warmer and then becomes back to 1, which sort of suggests at the bottom end it might tail off, and cold brittle is a problem for some metals, not all. But once you start getting really, really hot, it starts to, drop off as well. So if you've got a situation where you're running furnace tubes, right? So there are steel running hot under pressure, there might be cyclic loads through vibration or whatever, then you might really, really need to derate them in order to get a sensible estimate of their life. Reliability, again, straight out of a table. What's your chance that it's going to fail? And that's all, it's a chance of failure, it's not a guarantee, which is why we go 99.9, 0.99, 0.999, right? And the factors really significantly drop by the time you get to an almost 100% chance or guarantee it's going to survive. KF, I love this one. The miscellaneous effects, stuff we didn't think of to make a number up around. So the example they're showing here is if you've got a bit of case hardening on something, because what you can have is, a very hard case, sigma, it might be, let's say, handwriting is terrible on an iPad. Sigma ultimate equals 2 GPa, so really, really hard. By the time you get down to here, you might have, actually I'll make this a yield. Excuse me, I'm just going to do that. Let's make that 1500 MPa. By the time we get down into the core of the material, we might be back down to 700 MPa. And so what you might find is you exceed the yield strength of the base level material without exceeding the parent or without exceeding the case. And so you get a subcase fracture forming. So that's just one example, but you know, anything else you haven't thought of, you need to put it here in this KF. It's to remind you that you might need to think of other things. So, load fluctuates between -20 and 60, gives me a mean and a amplitude, which we can then start to plot. What we've done here is use that and added the tool, used the 2.5 to work out what that would be. So when we plot it on our graph, our Gerber diagram, it looks correct. So here we go over here. We've worked out what our endurance limit is, which is 104. We worked out where ultimate is. We can draw that. This is basically our sigma M, sigma A line, right? And we can work out from there what our yield strength is, or what our allowable stress is. And from there we can work out we need a 66 millimeter long weld, okay? Which, you know, you'd round that up to 70 in my books. No welder is going to be able to weld 66.0 millimeters. And you've got to think about the end effects. Part B is what if we really cleaned it up? And so Ka becomes a lot higher, 0.9. If we go back where we started this thing, Ka was 0.56, assuming an as-forged condition. Okay. So let's go back to where we were. Everything else remains basically the same, so we end up with a 35 millimeter weld. Again, I'd make that 40. So the important thing there is that surface finish can be significant. And it's why, in fact, you polish an awful lot of parts. For example, if you're building a race engine, you polish con rods to try and get rid of these stress precipitators. So again, on a Goodman diagram, we've increased what our endurance limit is, still come down to the same ultimate, we've still got the same ratio through here, so it allows us to work up to there instead. So again, very, very quick traipse across fatigue. It's a really large and critical area, but it gives you the basics of it. Okay.